All right, moving on to another form of transformation. These are reflections here. So I've jumped straight down to the investigation. And in the investigation, it says, consider the reflections and consider a transformation matrix A and the determinant of A for the reflection. And the first one says a reflection in the x-axis. So when we consider this one, if we have this point out here, which is x and y, if we were going to reflect it in the x-axis, so I'm just going to draw this so we can sort of identify where the reflection is. This isn't particularly great notation. What we're going to see is that for that to reflect like it was, like, you know, the x-axis is the mirror, we would expect the x-coordinate stays the same, but we've got a negative y-coordinate. And it'd be the same magnitude because you've got 2 units there, 2 units there. And so in this particular reflection, we're looking at, well, our x transformed is just equal to our x not transformed, but our y is equal to our negative y. So the transformation matrix for this, if we go back and think about x dash y dash equals, I should put this in, A, B, C, D, and then we've got our x and our y coordinates there. Okay, if we were thinking about this, let's just actually save ourselves some time later and paste one of them off. Okay, we're looking at, well, if x is the same, that means that our A value here has to be 1, B is going to equal 0 because we have no y coordinate, A times B, xy, B must be 0, and D here must be negative 1. D equals negative 1. So the transformation matrix for this particular transformation is going to be A equals, and it's going to be 1, 0, 0, negative 1. And the determinant of this matrix, which is the determinant of A in this particular case, is, let's just write the formula out so we can practice, AD minus BC, which means we're looking at 1 times negative 1 minus 0 times 0. And so we get a determinant here of negative 1. Okay, so that's our first one sort of done there. And we jump on to our next one because we're obviously going to be patterning this a little bit. So let's just get that up and we'll just copy that. I'm just going to get these in a space where we can see them in each example. Okay, so they're all there. And so the next one says a reflection in the y-axis. So in this one here, originally we did the x-axis. We're looking at our x and y coordinate here. Well, this would be no different to our first one apart from we get negative x and the y coordinate stays the same. So in this particular one, we'd be looking at, well, A must be, so, let's state what we're looking at here. So x transformed equals negative x and y transformed just equals our y coordinate, which means we're looking at, well, A here must equal negative 1. So we'd be looking at negative 1 here. B would be 0, C would be 0, and D here would equal 1 because they stay the same. Cool. Determinant again, I'm going to skip showing you the working, but that is negative 1 again because negative 1 times 1 gives us negative 1. Okay, the next one says a reflection in the line x, y. So let's just pick one here. And just so it's a bit more visual, I'm going to pick this coordinate here, which is x, y. Okay, but we're looking at this. This is 3, 3 and 1. Now, if I'm going to reflect this, realistically, that's sort of like if I come... I want to pick a different colour just so we can see it. So this is sort of like diagonally across one square. We're going to be sitting here in this particular one. So this new coordinate here, our transformed value there is going to be... You'll notice it's this becomes our y and this becomes our x here. Like they just flip if we rotate those coordinates. So this is interesting because we're looking at our transformed x value equals our y value and our transformed y value equals our x value. And so if we're considering this transformation matrix, then this means that A must equal 0, B here must equal 1, C here equals 1, and we're looking at this here gives us 0. So this gives us that value there, and interestingly again, our determinant equals -1 because 0 times 0 equals 0, minus 1 times 1, -1. So we've got another one there, and then our final one here is a reflection in the line y equals -x. So if we get this down here, and let's just pick the same value again. So this here at the moment is x and y, and I've picked that 3 and 1. So if we're reflecting in this value here, it means we're coming out here, because the reflection line will be the same on either side of the mirror, and it'll be a straight reflection. So this one here, you'll notice it's like the values we get, did I do that? We're going to get, well, this is like, whatever my x value here is 3, this is like my y coordinate is now -3. So I've got a y coordinate of -3 and an x coordinate of -1, which means, and I'll write them there and just do this because it makes the patterning a little bit easier. So this means that we're actually looking at like -y and -x here, which means the transformation matrix for this, we're looking at, well, x transformed equals -y, y transformed equals -x. So in terms of our transformation matrix here, we've got, well, this transformed x1 means a times x, we don't have an x in our equation, so a equals 0, but b equals -1. So we've got 0 and -1, and then my next value, c, well, c times x means that c must be -1 and d must be 0. And interestingly, again, the determinant of this equals -1. So as a pattern that we're seeing, if we're looking at a reflection, we're looking at a determinant of -1, but we end up with these values again. Now, I'm going to jump to the rule now because it's actually like we should be saying, well, 1s and 0s is a pretty good sign we're dealing with something trig-based, but in this space, I don't want to just give that to you. So our rule's actually a little bit more complex than that, in that we've got, for a reflection in the mirror line, y equals tan alpha x. Now, that might be a little bit confusing, but if you consider what your slope is, so your slope, I'm just going to pick this up, your slope m equals change in our y direction, which is this side of this triangle, or it could be the other way, and change in x. Realistically, that is the opposite of this side here. So if this is alpha, tan is opposite over adjacent. So tan alpha at x, the transformation matrix is given by these values here. Okay, and the determinant equals -1, which we sort of picked up. And if m equals tan alpha, then we have these identities here. Now, that might be a little bit confusing for the minute, but, and I don't think I made an example question for us. I've got an investigation later. So let's just do this one here. So we've got a question here, and I will read it out. I'll read it out. Let's delete this. You're watching me. Okay, delete that. Let's go here, and we're going to go. So we've done with that. So I'll just, for the transformation matrix, sorry, I'm just trying to do this quickly so we can still do the question. So A is in there, the transformation matrix A, and then we've got, in our text, we've got y equals 3x, which means, just so we've got this means 3 over 1x, just in case you were wondering in that space. Now, find the transformation matrix for the reflection in the line, y equals 3x. Well, realistically, we've got our transformation matrix up here. We've got this thing here. And so let's just copy that. No, we don't want to convert it. Let's copy that down here. So this rule, which we've not really, it's a little bit more complex because we're using double angles, and I know some of us don't particularly love trig. But that's why this is actually nice for us, is we're not looking at trig, we're going to use these identities we got here. So the cosine and the sine one, they're going to be our friends for this, so let's just paste them down here as well. So we've been given that m, our slope, equals 3, which is given here. And so we've got, realistically, in this particular one, tan alpha equals 3 as well. Just so you've got that in terms of this. And so that means our transformation matrix here, what we just need to do is we're going to go, well, cosine 2 alpha in this particular one means we're going to be looking at 1 minus 3 squared, because we're using this identity up here, over 1 plus 3 squared. 3 squared equals 9, so we've got 1 minus 9 over 1 plus 9, and we get negative 8 over 10, which is negative 4 over 5. Okay, so that's going to give us cosine 2 alpha here. We've got cosine 2, negative 2 alpha, so we're just going to put a negative sign in front of that. Let's just figure out our sine one. So we've got here sine 2 alpha equals 2 times m is 3 over 1 plus 3 squared, which gives us 6 over 10, which equals 3 over 5. So this means now that our transformation matrix here, how good, is going to be cosine 2 alpha, which is, I need to draw this bigger. Going to just need a bit more room for this one. So we're going to have cosine 2 alpha is negative 4 on 5. We've got sine 2 alpha is 3 on 5. And then we've got sine 2 alpha in the bottom left corner here is 3 on 5 as well. And then our last one here is negative sine, which is 4 on 5. And we've now come up with our transformation matrix for this one here, which means that if we draw this line of y equals 3x, we can reflect any 2 points in it quite easily using this. All right, I'm going to leave that there.